Hey class, Anova part 3, okay? So again, we're interested in finding the values of our null hypothesis. Well, let me rephrase that. We're interested to find out if our null hypothesis can be rejected or not. The null, of course, is that the means are different. However, I'm going to use SPSS to do this. So what's different about SPSS is that you have to put all of your data in one file, in one variable. So I'm just going to call this variable data for lack of better, and I'm going to call this one group. So your group variable is going to determine which group your data is in, and here's your values, and I'm just going to call 1 A, call 2 B, and call 3 C. So now, when I plug in my data view, I had 8, 11, and 5 in A. I had 10, 9, and 8 in B. And I had 7, 8, and 6 in C. And I want to identify these 3 as coming from A, these 3 as coming from B, these 3 is coming from C, and here's a label. So if I click this label, those 1, 2, and 3s turn to A, B, and C. Okay? That's our setup, and now we'll do our analyze, compare means, one-way ANOVA. Okay? Compare means, one-way ANOVA. Data is your dependent variable. Group is your factor. We don't have anything significant here, so I'm going to leave this alone. All right? And I'm going to click OK. We have our output, which we should be very familiar with. We have our sum of squares 6. Degrees of freedom is 2. 6 divided by 2 is 3, which is our first mean squared. We have 22 as our sum of squares for within groups, and 6 is our degree of freedom. 22 divided by 6 is 3.667 for our within group variability. And our mean squared we have is 3 divided by 3.667, which is this ratio of 0.818. And when you compare that to the critical F value, you have a significance level of 0.485. One of the differences with SPSS is that it will not show you the critical value, but it will give you the significance value. So what you can do is take this, copy this here, and look at what we have here. Now I just paste it here. Nope, sorry, I guess I didn't copy it correctly. I probably have to make it as a picture. Let's do. So I'm going to go back to my SPSS, click this, copy it, go to Word, a new Word, paste it as a picture, or actually just paste it. Alright, so I'm still not copying it. This time don't be difficult. Edit, copy. Good. I think I actually copied it that time. And I did. Then I can take this and put it on Excel, and you can compare your outputs. Okay. So what you notice from Excel, 6, 6, 22, 22, 28, 28, 268, 268, 3, 3.6, 3.6, 0.8, 0.8. P-value is significance value in the SPSS. They also give you the critical value in Excel, but not in SPSS. Okay? So you can come to the same conclusion using SPSS as well. Now back to the SPSS, because this is something that we did in class that didn't really seem to make sense to me. You know, we made it where these numbers were relatively close, and then we decided to just go ahead and change one number outlandishly large. And I'm going to do it again. So now I have this 3,000 in here, and when I redo my analysis, I'm going to show you what you end up getting. Okay? So I did it again, and you see the significance was still not significant. The F went up slightly, but the means were one definitely looked bigger than the other, but it's not significant. And so originally we thought we made some error, but then you have to realize that we're only looking at 3 values of each group. So your sample size is small, so that's why this isn't significant. And just to bring that point home, we actually did another example that you guys are probably familiar with. And I'll open that for you if I can find the data. And then you'll see what happens otherwise. Aha! So you guys remember that cars file? And so I'm going to open that cars file here. And let's assume that we're looking to find out, is there a difference in the price of cars based on the cylinder size that they have. Okay? So you have three cylinders, 4 cylinders, 6 cylinder, 8 cylinder. And the price variable is somewhere down here, which is anywhere between 15 and 33,000. Okay? So you can't do this with Excel very easily, but you can do it with SPSS. So I'm going to rerun Anova in this case. My dependent variable is going to be price. So I want to know, is there a difference in price? And my factor is actually going to be cylinder. So I want to know, is there a difference between 4, 8, and 6 cylinders? I'll click post hoc, and just for argument's sake, I'll click one of each. Okay? Actually, game style is probably better at this point. And click continue. Okay? So I want to find out, is there a difference in price based on by the cylinder, depending on cylinder type. Click OK. I have output. Okay? Here is one of the first times you actually saw a significance value that's less than 0.05, right? So the way you read this Anova table is exactly the same as before. Here our degrees of freedom is 4 because we had 5 groups, maybe? So if I look back at cylinder type, we must have more than three cylinder types. So frequency of cylinder. I'm only familiar with 4, 8, and 6. I wonder what the other ones are. There were some 3 cylinders, some 4 cylinders, some 5 cylinders, some 6 cylinders, some 8 cylinders, and there were some that were missing, and so we just left those out of the calculation. So there were actually 5 different types of cylinders. 5 minus 1 is 4, and that's where you get the 4 from. Okay. Here, we go back up here. Our within groups, we had 92 values that had cylinders. 92 minus 5 is 87. So that's our within groups degrees of freedom. And when you add the two together, you get 91. So now when you're looking at your F-test, we have a very large between group and a relatively moderate within group. Gives you a large F, which makes this significant. Now the thing that's really interesting is, why would you want to have a large between group and small within group? If I have a large variability between groups, that seems to suggest that you have distinct groups. The further away these different groups are, the more likely you have distinct groups. But if I have a group and it has a very large variability within the group, then they're saying there's a lot of variability in your data. So even if I'm saying I'm one group, but now I have all this variability, then it's not, how much of a one data is there? So if you have a large between groups, that's evidence of kind of a distinction between one group centroid, another group centroid, another group centroid. There's some distance between them, which makes it seem like they do not overlap. Because if the actual groups tend to overlap in this theoretical space that you can't visualize, but if they overlap, then there's no difference in them. Okay? So you want to have a large between groups, a relatively small within groups, because then you'd have homogeneous groups, and you end up with a larger significance level. So here we're looking at 91 values. So we have a crazy number here, looking at a number with 10,000 or whatever, but we're only looking at it with 3 degrees of freedom, or with 2 degrees of freedom, really. So no matter how big it was, you really don't have enough confidence to say, yeah, this is something real, which is why we continuously failed to reject the null in class. But had we looked at our data and did it on data that was longer, 50, 60, 70, 100 different values, you can see the likelihood of making a significant finding is better. Okay? So now since we know it's significant, we can look at the post hoc test to find out which ones are in fact different. Okay? So one of the things that I did not do in this case, which I probably should have, was to find out if the variances were equal. So I could have done a Levene's test to find out if the variances were equal, but at this point I'm kind of taking a guess. If they were unequal, I would be reading this LSD one, but if they were equal, I'd read LSD. If they were unequal, I'd read the game's howl. But here's how you read it. Okay? What this group is doing is comparing each of the values to each of the other values. So basically, it's looking at the difference between 3-cylinder and 4-cylinder, 3-cylinder and 5-cylinder, 3-cylinder and 6-cylinder, 3-cylinder and 8-cylinder, and the mean difference is given to you as I minus j. So that's 3 minus 4. So a mean difference of 6.18, which is negative, means that the 4-cylinder car, on average, costs $6,184 more than the 3-cylinder car. Okay? But when you go across, you see the significance level of 0.161. That's not significant. So the difference isn't significant. Again, you can look at the confidence interval and see that it includes 0. It's not significant. But when we compare it to the 5, 6, and 8-cylinder cars, there's a difference of 14,700, 15,919, and 25,319. These differences are in fact significant because you notice there's no 0 included. So you can say with 95% confidence that the mean price for a 3-cylinder car is different than, or even less than, since you have the confidence interval, the mean price of the 5, 6, and 8-cylinder cars, but not the 4-cylinder car. Okay? That's one row. We'd have to do it 4 more times. Okay? So here with the 4, we're now comparing 4 to 3 and all the rest. But notice 4 to 3 is exactly the same as 3 to 4, except the sign has changed. So we don't have to interpret the 4 to 3. We already know that that difference is not going to be significant. But we can look at 4 to 5, 4 to 6, and 4 to 8. 4 to 5 isn't significant either, even though it was $8,500 less. But from 4 to 6 and from 4 to 8, it is in fact significant. You'd see that from 4 to 6, it's about $9,740 cheaper. And for an 8-cylinder car, it's $19,135 cheaper than an 8-cylinder car on average. Notice the p-values are less than 0.05. Also notice the confidence intervals do not include 0. Now we've done 3 and 4. Let's look at 5. Okay? 5 and 3 is the same as 3 and 5, just backwards. 5 and 4 is the same as 4 and 5, just backwards. So the only new ones we have to look at is 5, 6, and 5, 8. Okay? 5, 6, not significant. So it's only about $1,200 less anyway. And 5 to 8 is $10,619 cheaper on average, but it's not significant. You notice it includes 0 because you have this positive 1 here. So 5 is significantly different from 4 and 3. Nope, sorry. 5 is significantly different from 3, but not 4, 6, or 8. Finally, well, not finally, but almost finally, we have 6. 6 has already been compared to 3, 4, and 5. We know it's significantly more than 3. We know it's significantly more than 4. It's not significantly more than 5, right? But it is significantly less than an 8-cylinder car. So an 8-cylinder car is about $9,400 more expensive than the 6-cylinder car. And that is in fact significant. Okay? So once I have 3 to 8, 4 to 8, 5 to 8, and 6 to 8, this one is just a repeat of all these other 4. So I don't have to interpret it. But if you're interested, you can see that 8 to 3 is exactly the opposite of this one. 8 to 4 is exactly the opposite of this one. 8 to 5 is exactly the opposite of this one, if I move that out the way. And 8 to 6 is the opposite of this one. So in conclusion, the 3-cylinder car is cheaper than the 5, 6, and 8-cylinder cars. The 4-cylinder car is cheaper than the 6 and the 8-cylinder car. The 5-cylinder car is more expensive than the 3, but it's not more expensive than 4, 6, or 8. The 6-cylinder car is more expensive than 3 and 4, but it's less expensive than 8. Okay? And the 8-cylinder car is more expensive than all of them except for the 5-cylinder car. Now, it kind of makes less sense to me why you would have a insignificant 5-cylinder but a significant 6-cylinder. Now, you can think of it from a statistics standpoint or a logic standpoint. Okay? From the statistics standpoint, perhaps there was a smaller sample of size 5 to 8, so I didn't have enough degrees of freedom, which means I didn't have enough power to find this to be significantly different. But from a practical standpoint, it could be that a 5-cylinder car is so hard to come by that it is in fact more expensive than a 6-cylinder car, which is a dime a dozen. So that could possibly be the case. I do not know the answer. I just find that's kind of interested in this data set. Okay? Once again, this is interpreting, assuming that there were equal variances. If there are unequal variances, you would use a different one, but the process looks similar. Okay? So you'd say 3, 4, 3, 6, 3, 8, 4, 3, 4, 6, 4, 8, nothing for 5, 6, 3, 6, 4, and 8, 3, 8, 4. Okay. So the takeaway here is that if I have a large enough sample size, I can find something significant. It's more likely that I will, in fact, find it significant. All right, I'm going to stop this here, and the next time I have a video, we're going to look at how I would look at the F-test. Actually, you know what? I should be able to bring an F-test up right now. Nah. Yeah, I'll do it now. Okay. So we're going to go back to this one. Okay. And we have these values here. And we had an F statistic that was based on 2 and 6 degrees of freedom. So we're going to try to find an F statistic on the internet, and then I'll show you how to read it. So I'll be right back. All right, class. So I was able to find an F table. Okay? The way you read an F table, and this is a little bit different than in your book, but it kind of says the exact same thing. The row headings, in other words, the ones that say degree of freedom 2, 1, 2, 3, 4, 5, 6, 7, etc., is the denominator degrees of freedom. So this is the degrees of freedom of your within groups, or your n minus k. Okay? In our example here, we have 6 degrees of freedom, so it's 6 is what we'd read here on the row. The column headings is your first value. Your first degree of freedom is your between groups, which is k minus 1. So 3 minus 1 is 2, right? So I'd look for 2 degrees of freedom. Right? Now this one test, this one table here, gives you the value only at 0.05. But the one in your textbook, if I'm not mistaken, actually gives you values at 0.05 and 0.01. Right? I do believe they do so. You can look at page number look at page 454 in your textbook, and they give you numbers at the 05 and the 01 level. Okay? But this is just an 05 that I found online somewhere. And what you would do at this point is look inside for the number. So if I go over to 2 and I go down to 6, I have 5.1433. This is the critical value that I compare my F to. And again, 5.133 you see here. You also see it in your SPSS output as 5.143. If we were looking at the other sheet, we have 3 degrees of freedom and 20. Okay, 3 and 20. What I'll do is actually bring over this picture for the other one. Okay. So 3 and 20 is what we're looking at. Too far. If I go over to 3 and go down to 20, this is 1, 2, 3 to 20, I see 3.0984 right here. And when you look at F, you'll see 3.0984. So basically, to read the F table, you need 3 pieces of information. You need your between degrees of freedom, which is your numerator. You need your within degrees of freedom, which is your denominator. And you need your confidence level, your significance level. And that's where you get your critical value from. Okay? I think I've covered all of ANOVAs, including your homework answer. So that's it for me. Next time we talk, I'm not even sure what we're looking at, but it won't be ANOVA stuff. So talk to you soon.